This is the simply supported beam setup which will be used for verification of Maxwell's reciprocal theorem and verification of principle of superposition methods for a simply supported beam. Okay, you can see the simply supported beam resting on knife edge support. So the length of the beam is 780 millimeter, and you can see the cross section here 16. Okay, the width is 16 millimeter and the depth is 6 millimeter. It is made up of mild steel. The Young's modulus value is 2 into 10 power 5 Newton per mm square. So, according to Maxwell's reciprocal theorem, the theorem states that the deflection at 1 due to load at point 2 will be equal to the deflection at 2 due to load at 1. So, according to that theorem, in this beam, we have marked 2 points. You can see here we have marked 2 points. Let us take, the left hand side, dial gauge is fixed. Let it be 0.1, and right hand side, anchor is fixed. Weight anchor, which is nothing but 0.2. Okay, so in the anchor we are going to apply the load and we are going to measure the deflection in the dial gauge. Okay, so here in the beginning, before setting this setup, we need to make sure that the needle is at 0 position. Once when the load or once when the weight is added, the needle gets deflected and the readings are noted in the tabular column. And also the vice versa, if you just replace this dial gauge with the anchor, weight anchor, and the weight anchor by the dial gauge, you can find the deflection at 2 due to load at 1 and enter the reading in the tabular column. And we can verify this by theoretically also.
Already we have seen beam setup in video, how to take the readings for Maxwell's reciprocal theorem experiment. Okay, again let me explain. Okay, so we have marked 2 points, point 1 and point 2. At point 1, dial gauge is fixed. At point 2, weight anchor is fixed. We will add the weight here at point 2, and at point 1 we measure the readings in the dial gauge. We are going to add the weights in the range of 500s. For example, reading 1, we are adding 0.5 kg. Then we note down the readings in the dial gauge. Again, add another 0.5 kg at point 2, measure the reading in the dial gauge. Again, you add 0.5 kg, measure the readings in the dial gauge. Like this, on the range of 500 grams, we measure the readings and note down in the tabular column. So this is nothing but deflection at 1 due to load at 2. Similarly, now just interchange these two, shift this weight anchor to the dial gauge position and shift this dial gauge to the weight anchor position. So now you add the weights same way, same range, same 5 readings, like 500 grams, or for every 500 grams at point 1, measure the readings in the dial gauge at point 2. So this is nothing but deflection at 2 due to load at 1. So enter the readings in the tabular column. So we must know how to note the readings in the dial gauge. Now, for example, this is the dial gauge and this is the point of contact. So this will touch the undersurface of the beam. So this is the point of contact. Okay. So you can see the dial gauge is graduated. So from 0 to 100, the bigger one. Here you can see here 1 to 10. Okay. If this smaller pointer moves or rotates through from 0 to 1, means the bigger needle would have been taken 0 to 100, one complete revolution or one complete rotation. Okay. So once when the weight is added, this pointer, the bigger needle or the pointer, gets deflected or rotated, for example, from 0 to 20 position, 0 to 20. So what would be the deflection? So dial gauge indicator shows 20 in millimeter 20 into 0.01 millimeter, that is 0.2 millimeter. If it exceeds, for example, if the bigger needle exceeds, for example, undergoes one complete revolution and it comes to 120 means this small needle would have been moved from 0 to 1. That means 120 into 0.01, 1.2 millimeter is our reading. So like this only we have to take down the readings from the dial gauge. So this is aim apparatus required, and the dimensions already I have just posted in the video. So this is a theorem. Okay, so deflection at 2 due to load at 1 will be equal to the deflection at 1 due to load at 2. So this is what we are going to prove it, okay, experimentally as well as theoretically also. So this is a procedure, as I told you, procedure. And what we'll do is we will note down the readings. We will find the average of those two readings. I'll tell you what is that average. Okay. For unloading and unloading, we will be calculating the readings. We will take the average deflection of this unloading and loading. Then we'll convert that readings to millimeter. Then we will plot a graph between the load and the theoretical, which is in millimeter. That is a kg versus millimeter for those two cases, that is delta 1,2 and delta 2,1. We will try to find out the slope of these two cases, and if the slopes are equal means Maxwell's reciprocal theorem is proved. Okay, so this is the tabular column for delta 1,2, that is deflection at 1 due to load at 2. Okay, deflection at 1 due to load at 2. We are adding 0.5 kg weight. We are noting down the reading 40 in the dial gauge, then 1 kg 79, 1.5 kg 116. Like this we note down the readings. So once we come to this fifth reading, so let us go for unloading phase. So it starts from 2.5. Okay, at 2.5 191 is the reading. Now remove 0.5, you will get 2 kg. For that 2 kg, what's the reading? So like this we reduce the weight by 500 grams, note down the readings in the unloading column. Then this average delta 1,2, we take average of these two readings, and we will convert this to millimeter, that is multiplied by 0.01. You will get 0.41, 0.79, 1.16, 1.55, 1.91 millimeter, like that. So for 0.5 kg 0.41 millimeter, for 1 kg 0.79 millimeter, like that. So in the plot, kg versus millimeter, you have to convert to millimeter. That we are using for drawing the graph. Straight line, you will get a straight line. For the straight line, you will find a slope like y is equal to mx plus c equation. You will get, if you use the plot, if you used to draw the plot in a software means, you can get the straight line equation. And delta 2,1, okay, now deflection at 2 due to load at 1. Now we add the load at 1.5 kg, you measure the deflection. So like this you repeat the experiment for 5 readings. Similarly, unloading process also. Then you find the average multiply 0.01, you will get deflection in millimeter. Then this load versus this average, plot a graph where's the graph for delta 2,1 case, and try to find out the slope. So the slope for delta 1,2 and delta 2,1 must be equal, so which proves the Maxwell reciprocal theorem. So here I have plotted with MS Excel plot. So I have converted to I have converted these average readings into millimeter. Even if you're not converting, no matter. If you're not converting means this will be, slope will be 75. Okay, y is equal to 75x. Here y is equal to 75.2, something like that. So you can see here the slopes are same for both the two cases. So delta 1,2 is equal to delta 2,1. And I have done this numerical verification also by MAXWELL'S method. So this is the beam. I have taken 2 random points at different locations. Same way, I have assumed some load 100 Newton acting at 0.2, delta 2,2, deflection at 2 due to load at 2, delta 1,2, deflection at 1 due to load at 2. We have got the equation, Maxwell's equation. Then we have at x is equal to 1 meter, substitute in this equation, you will get the deflection y1 is equal to this one. Then interchange the weights same way, get the Maxwell's, by Maxwell's method, get the expression for deflection at 2, x is equal to 1.5 millimeter, y2 is the deflection. So which is equal, y1 is equal to y2. So it is observed that Maxwell's reciprocal theorem is proved.